So chapter 2, we're kind of doing in one, not lesson, but one section. So we're going to spend today's class and tomorrow's class on this chapter. The concept behind this topic is motion. We're looking at motion. It's the beginning of physics. It's like the real first thing we're going to do that's physics oriented. In the last class, if you recall, we did a lot of unit conversions. We did some stuff with scientific notation as well. So that material was kind of a refresher from your chemistry course last year. You should have seen some of that stuff, at least at the minimum. So this is going to be our first real look into physics this time. So we're going to talk about some key terms. We're going to use terms like displacement, time, velocity, speed. We'll talk about distance. We'll talk about how displacement and distance are actually different things. We'll look at graphs. And then we'll specifically start off right now with frame of reference. So let's begin with that term, frame of reference. So this is really important because depending upon your frame of reference, your answer in physics is different. For example, if I was standing still right here, right now, you would say that my velocity is, I'm standing still, 0. And I would agree with you. My velocity with respect to this floor is definitely 0. But we all know that the Earth is doing what? It's rotating, right? And it rotates real fast. Something like 23,000 miles per hour. That's the speed at which you rotate tangentially. You're sucked to the Earth because of gravity, so you don't feel it. But physically, the Earth is rotating. While it rotates, it's also revolving around the sun. So frame of reference is important because if I ask you the same question again, and I said, what's my velocity with respect to Mars, I have a velocity. Because if Mars is here, and the Earth is here, and the Earth is moving, and I'm on the Earth, I'm also moving. It's like when you're in a car. If you're in the car, yeah, the car is moving, but you're also moving because you're in a moving body. The car itself is traveling down the road. You might say, your parents might say in the back, sit still back there, like you and your brothers, or you and your sister, stop screwing around in the back seat, my dad always says. Stop screwing around in the back seat. And if he says sit still, you can say, I can never sit still, I'm in a moving body, I'm always in motion, There's a million of these things. I even said to the class, I said, if you're going to pull over, stop sign, use that. They say, you need to complete stop. I said, well, officer, are you ever ready to complete stop? Right? No, you're not going to take it anymore. Do not try that one for real.
I really want to.
If you do, though, let me know how it comes out. I'm curious to see how that turns out. I've always said there's always a physics answer to every single ticket you can get for a car violation or a moving violation. You could have some sort of stupid retaliation in physics and argue yourself out of it. Yeah. Speeding tickets, yeah. Exactly. Well, sir, we're revolving at 23,000 miles per hour, so we're all breaking the speed limit. So anyhow, your frame of reference matters. If you personally imagine this, give it a scenario, you're on the 456 train, you're coming up to school or coming downtown, depending on which way you come from, or the Q train. You're on the train, and the train is moving. Trains move pretty quickly, actually. So the train is moving at like 50 miles per hour. And hypothetically, you're like, ooh, you know what, at the next stop, if I go to the next car, I'll be closer to the exit, and I'm running late for school. Have you ever done this before? You move up train cars as the train is going, so you're closer to the exit because you know where it is. So what if you're moving on a train that's also moving? Well, the train is moving at 50 miles an hour. You might be walking at like 1 mile an hour, 2 miles an hour. So your velocity with respect to the platform or the bystanders at 68th Street as you're passing them on the express, they see the train moving at 50, but because you're moving at 2 miles an hour, it looks like you are moving at 52 miles an hour. It's the same thing as when you're in an airport. Remember when you're in an airport, you go on the moving walkways? And as you move on the walkway, you can walk, right? But when you look next to you, it looks like you're running. It looks like everything's passing by pretty quickly. Because not only is the floor moving at, say, 2 miles per hour, you're also moving at 3 miles per hour, whatever it is. The sum of those velocities is your apparent motion to bystanders. So this is all, again, with respect to frame of reference. It matters what your frame of reference is. Okay, your frame of reference. If somebody is next to you on the moving walkway, you both seem to be standing still to each other, right? If I'm standing here and Sydney is right here next to me and we're on a moving walkway and we're having a conversation, we don't feel like we're moving with respect to each other, and we're not. We're literally the same distance apart. But with respect to the ground next to us and the bystanders, they see us as objects in motion. So frame of reference is pretty big. I'm not going to hound you on it. Like, I'm not going to say, like, what is your frame of reference or what is your velocity with respect to Mars? I have to figure that stuff out. That's more advanced dynamics and astrophysics and college would take. But I want you guys to recognize that when we talk about things, we're talking about being on a stationary Earth. When in reality, we are never on a stationary Earth. Okay? But that's what we're referring to things as if we're on a stationary Earth, but we're not actually there. In the window? Maybe it'll help a little bit. It's probably hot back there. Do you guys want to open that window a little bit? You okay? If you can get to it. I don't know. It might be in the way. The second phrase we're going to go into, you kind of have to pull up on both sides at the same time. It's team effort. Or it's just chance. Don't just let it go. Sorry, guys. I thought that would open. So the second phrase we're going to use here is displacement. And displacement specifically refers to an object's change in position. Object's change in position. So if I look at this gecko here, it was a gecko. We started here like 24 centimeters or meters or inches, whatever these units are. They're arbitrary right now because there's no units. And he or she, as a gecko, is ending around 84. So starting at 24, ending at 84. What's the overall change from 24 to 84? What number? What would I say is the difference between those two? 60. So I could easily see that the gecko has displaced 60 meters or 60 centimeters or 60 inches. But the concept here is this. If I want to know what displacement is, we're going to use x as a variable here. I take the final position and subtract the initial position. And I take the current position, the position at any moment in time, and subtract from that the initial position. That is my overall displacement. So this gecko could have started at 0 and ended at 60. Or it could have started at 30 and ended at 90. And those are the same displacements. Either way, he or she travels 60 units across the page to the right. So displacement is a function of your initial and final position. Your initial and final position. So, for example, if I walk, follow my path please, I'm going to walk toward the shop vac, right? Say about 5 meters, estimate, so maybe draw a line 5 meters. And then I'm going to make a right turn 90 degrees and walk toward Chris, another 5 meters. And the question posed might say, what is the displacement of the object? Or what is the displacement of me as an object? So if I walked 5 meters this way, and then I walked 5 meters that way, and my definition of displacement, it again, is the change in position from final to initial. Well, here's my initial, here's my final. What would be my displacement in this kind of a problem? What would be my displacement? So initial position, final position. What would be my overall displacement? You don't have to give me an exact number, but tell me how you would do it or what you would do to get it, Alex.
Can you just be triangle sort of? You just use the distance formula?
Yeah, or in this case, yeah, Pythagorean theorem. Very good. Pythagorean theorem, distance formula. So in this case, because I said a right turn, remember I said like a right angle, what we have is a right triangle. So if an object moves north and then it moves east, or if it moves south and then east, you can connect the beginning and the ending spot, and that is your overall displacement. So when you think of displacement, I want you to think back to when you were a kid and you learned this. Everybody did in like some sort of math or science class. You learned that the shortest distance between any 2 points is a straight line. Very good. Straight line. So displacement is really just that. The displacement is the physical shortest distance between 2 locations in space. Now, what would the exception be? What would the exception be? When can you actually get from A to B in a shorter path than actually walking directly there? It's not real, but theoretically, what would the exception be? Theoretically, it's science. Good. A black hole, a wormhole, something that takes you from one point in space to another, and you elapse no distance, but somehow you end up in a different spot. Teleportation is really what we're talking about, right? Teleportation. Do we have any Dragon Ball Z fans in the room? Anybody know of Dragon? I feel like it's dying out over time. I reference it every year, and fewer people watch the show.
We know it. Yeah.
You know of it? You've seen all the Goku memes and all that kind of stuff? Yeah, Super Saiyan stuff. When I was a kid, it was like, I watched it as a kid. It was a cartoon. There is so much crazy science in that show. So I do tend to reference it sometimes. And in the show, we learned how to teleport from like one galaxy to another. I don't know how he did it, but it's obviously science fiction. But that idea would be taking this concept and invalidating it, right? Again, the shortest distance that we know from A to B is a direct straight line. Now, if this object moves along the path and you measure that, this is called the distance traveled. Okay, so let's write that down here. That the distance traveled, we'll say D is for distance, and X, as we said, is for displacement. And the distance traveled is the path taken. The displacement is the, I'll say straight line. Okay? So the distance traveled in this example right here is 10 meters. The path taken is just the length, or the displacement, the path taken, the straight line is the length of the hypotenuse itself here. Anybody know the special triangles for that? What would that length be? 5, 5. Anybody know the hypotenuse? It's a 45, 45, 90 triangle. 5 root 2. Do you remember this? X root 2. Think back to the geometry where you had like for the 30, 60, 90, it was S, 2S, and S times radical 3. Yeah? So this is just the length of 5 root 2. So again, for this problem here, our displacement was 5 root 2. When the distance traveled is actually 10. And again, I didn't indicate units on this problem, so I'm just arbitrarily using these numbers. In examples, you will definitely have actual units that you need to utilize. So for now, if you want to call them meters. Right? It doesn't matter what you use in this case. You could use feet, you could use miles. We don't know what the object is, so there's no context of the problem here. I don't have to say, oh, miles wouldn't make sense. It's an ant, and the ant is traveling on your desk. Then an ant's not going to walk 5 miles, right? Maybe a human being or a car could go 5 miles. So the units are arbitrary for now. So distance and displacement. 2 different things, very easily misconstrued or misinterpreted. Okay, a lot of students think they're the same thing, and they're very different entities. And we're going to see how they play a role in a little bit. Let's go on to the first example here. In the first example, we've got a space shuttle. And a space shuttle takes off from Florida. Let's say Cape Canaveral, I think is down there when they take off. And circles the Earth a couple times, maybe doing some sort of research, studies, whatever, and lands in California. At the same time, while this is happening, a photographer gets on an airplane, flies directly from Florida to California. Does not circumnavigate the Earth several times like the space shuttle does. Just goes directly from Florida to California. And the question posed here is who, out of these 2 people, the astronaut on the space shuttle, or the photographer, who undergoes the larger displacement in this problem? Who, and give an answer of why as well. Who and why? What do you think? Some of us, once you answered a couple of questions. I like the participation though, so I'm just trying to mix it up. Who undergoes a larger displacement? Take a stab at it. What do you think? Maybe draw a diagram if you don't know, right? Draw a diagram. Good.
Maybe the space shuttle.
Why?
Going around the Earth at the time while the Earth is moving like around the sun. So I think it's
The space shuttle is definitely taking a longer path. Agreed? Absolutely. The space shuttle is definitely taking a longer path. But, Zoe? Probably. Let's assume it's not, but I like that. Yeah, if he says the Earth is moving, it could affect it also. But it wouldn't matter whether the Earth is moving or stationary to actually answer this question. So you don't have to worry about that. I'll say that that's not even needed for this problem. You want to help out? Do you have a different answer you had, or do you have the same answer?
the photographer because he's not leaving the atmosphere.
Is not leaving the atmosphere? What does that make it? How does that make a difference? Explain your argument.
Well, because he's I just like know it's that thing, but it's how to explain it.
Other arguments? I've heard 2 arguments. Bridge?
Would it be like the same if they both, if their initial location and their final destination is the same?
What's the definition of displacement? It's kind of a trick question, I know. And it's just to get you guys thinking outside the box right off the start of the year. The initial position is where? Everybody, where's the initial position? And the final is? and it's no different for either of them. So you started it.
Straight line.
Yes, and you started answering the question. We had the idea that as the astronauts circumnavigate the Earth, they're traveling a long period of time and a long distance. A long distance. But what does the question actually say? Displacement, not distance. So if I'm visualizing this, here's the Earth. Astronauts ending in California. Photographer going directly from Florida to California. So the photographer's trip is in yellow. He or she goes right from Florida to California. The astronauts circumnavigate a couple times, end up in California. But from start to finish, if we're looking at overall displacement and comparing the two, they both displaced the same amount of space. They both displaced the same amount. Okay, because again, all that matters for displacement is the physical straight line distance from A to B. And I'm using the word distance there. I know, it's not a mistake. Again, for displacement, all that matters is the straight line distance from A to B. The path taken has no effect. Kind of the opposite of what you hear in Jesuit schools, right? All about like the journey taken is what matters. How you get through school and how you change over time and develop is really, and it is. It absolutely is. Here, it's not. The path taken has no effect whatsoever on this actual displacement. Okay? Yeah? So if I walk around the room like 7 times and end up where I started, literally 7 times, what's my displacement?
0.
0. Because where did I start and where did I end? In the same position. Okay? My distance traveled is whatever length of the path I took. But if I start and end in the same position, my displacement is actually 0. I haven't physically, well, I haven't technically moved, I should say. Physically, I have. I've taken some sort of a weird path. And you've all done this before, right? Across Central Park. There's no direct line, really. I mean, there are a couple that are close to it, but there is no physical direct line across Central Park. You have to take a different route. And if you drew the direct line, you would see the actual displacement that the object undergoes. Okay? All right, let's keep going. Let's keep on going. So we can classify displacement 2 ways. Displacement can be classified as a negative displacement or a positive displacement. And what we're going to do in this course is adopt a simple notion. Follow your Cartesian coordinates, your xy axis. Think about on your xy axis, up is always positive. So in this course, we're going to consider up positive and down negative. We're going to consider to the right positive and to the left negative. That's going to be our standard adopt. This is going to be the rule that we're going to adopt in this course. You could think of it differently. It's completely arbitrary. I could say down is positive and up is negative. And all year, you're going to have to think of everything down as positive. But it's probably going to be a little bit, counterintuitive because in your math course, you would think of it the other way. So I'm going to try to be systematic here and keep it the way you see it in your math class. But again, it could be any way you want to think about it because it's arbitrary. Think about this. It's a little philosophical for you. We're on the Earth, so we know north, south, east, west, right? Does that make sense? But really, what's north, south, east, and west when it comes to the universe? Think about that for a second. The universe is ever expanding, infinitely large, right? We're talking about things that we are a minuscule speck of dust in the real big picture of the universe. So if you're out in outer space, what's up and what's down? What's left, what's right? You know what I mean? That adoption of directions doesn't actually apply in that sense. So because we are taking this rule of up is positive and right is positive, we're going to be sticklers about it in this class for physics, specifically on the Earth. Okay, Chris?
Wait, so outside of Earth, what do you mean like the north, the whole compass could change? Like, since we're always kind of moving?
Exactly. The Earth is, first of all, the Earth is tilted too. It's on a 23.5-degree axis. So it's spinning like this. Literally, as it goes around the sun, it's spinning on a weird-looking axis. Well, here's our North Pole. Does that mean that out here in the universe is north and down here in the universe is south? No, it doesn't. So we use stars and celestial bodies to orient ourselves. Stars, other galaxies. That's, again, more astrophysics, a college physics course that you could take once you've taken a basic physics course to learn about physics on the Earth, for the most part. Good question, though. Yeah, there's no right or wrong answer. So let's look at these examples real quick. So this is like, an object moving. In all of these cases, it doesn't matter where the object, look at where I'm pointing here. It doesn't matter where the object started. All 3 of these cases, the object is moving to the right. So the displacement has to be positive. And remember, displacement is final minus initial. So I'm going to zoom in real quick so we can see this a little bit better. Let's look at the first example. It looks to me like this object starts at 10 and ends at 80. Final is 80. Initial is 10. 80 minus 10 is 70. Is that agreed? Is that pretty simple? We go to the next one right below it. We take a look at the next one to compare it to. This object starts at 3, ends at 12. Final is 12, initial is 3, 12 minus 3 is 9. Still rather straightforward. The third one is the one that sometimes people get confused about. Well, you know what? This object started all the way back here at negative 10 centimeters and ends up at positive 6. Even though this is a negative starting value, it doesn't make your displacement negative. Because which way did this object travel? To the right, which is positive displacement. And do the math. Final is 6 minus initial, which is negative 10. Double negative makes it a? So it's really 6 plus 10, therefore, the displacement is 16 centimeters. Keep the number line in the back of your head when you're thinking about displacement in this class. Okay? Keep this picture in your mind. Now, in this chapter, and in chapter 3, actually, these two chapters, we're only going to be working on horizontal motion. Okay? Or, next chapter, we'll specifically look at just vertical, but not at an angle. When we get to chapter 4, we'll start looking at like projectiles, missiles, soccer balls punted, a football punted, a baseball thrown from the outfield. Anything that you would literally launch at an angle is a projectile. Now, we are looking only at things moving linearly, left to right. In the next chapter, only up and down. Okay, so for this chapter, though, x is going to be our displacement variable that we'll use to represent motion left and right. So on the other side here, we have 3 examples of negative displacement. I'll go a little quicker here. This guy starts at 80, ends at 20. So final is 20 minus the initial, which is 80. It's a negative displacement. Again, here, starting at 15, ending at 0. So ending is 0, which is there, minus the initial, which is 15. 0 minus 15 is negative 15. Again, motion is left, displacement is left. And the same thing for the third example here at the bottom. Okay? This object starts at negative 10, ends at negative 20. We take the final, which is negative 20, minus the initial, which is negative 10. There's a lot of double negatives and negatives going on here. We got negative 20 minus a negative, which is really plus. So negative 20 plus 10 is indeed negative 10. But you should have a common sense check for all of these kinds of problems. If an object is moving to the left and you get a positive displacement, something's wrong, right? You did something wrong with the math, with the simple algebraic or arithmetic that you're utilizing here. And if you made a mistake and you got a positive answer, you got to do a quick sanity check on these tests. And I also talked about that, if you recall, with like number sense. Right? If I ask you for the mass of a shoe, because the shoe is moving across the floor and it's friction that's stopping it, I mean, the mass of a shoe should be like maybe a kilogram at most. That's 2.5 pounds, or 2.2 pounds. A shoe that's 2 pounds is a pretty heavy shoe, I guess, right? So maybe like a fraction of a kilogram. So if your answer comes out to be multiple kilograms, that's not really sensible. Doesn't make sense. Same thing here. Okay, if it moves left, it's got to be a negative displacement. All right, let's take a look at our first formula for the year. First formula for the year. One thing I want you to note right away here is that this is always going to show the units. I use brackets to indicate units. So write yourself a little note that these are the units for average velocity. And they make sense. When you drive a car, what do you measure the speed in? When you drive a car, what is it in? The speed, not the distance. Miles per hour, right? Miles per hour. Well, take a look. Meters per second. Similar, right? SI units instead of miles per hour.
Wait, you said these are the
Dimensions or units of velocity. And speed, turns out, is going to be similar as well. Speed and velocity are both measured in meters per second. Meters per second. And try to get out of the habit of writing MPH for miles per hour, or some people in the past have written MPS for meters per second. Try to get out of that habit. Okay, write it this way where you actually have a fraction bar. And you'll see why. Because when you start to cancel units and do a little bit more involved physics, the units will matter, and showing the fraction actually helps. So try to get out of the habit of writing MPH or stuff like that. What does x represent, like we just said? What does x represent?
Displacement.
Good. Displacement of the object. That's this first part of the, that's this first part of the formula here. That's this. And then over in math means what? What does over actually mean? Fraction, very good. Divide, well done. And over a given time interval. And that's the denominator, the time interval. Okay? So again, we've got displacement over time. Displacement over time. And that will give me the average velocity. This is not the same thing as my current velocity. And let me give an example of this. Let's say, all right, how many of you run cross country? Cross country runners, we have a couple? All right. So in cross country, when you have a 5K, are you going to sprint out of the box? Probably not. It doesn't make much sense to sprint right out of the, not the box, out of the, what's that called? The thing that you put your feet on in a track race sometimes? Blocks, thank you. You're not going to sprint that. There's no blocks for cross country. I know it's track, sorry. But you're not going to sprint right off the bat. Why not? Why aren't you going to sprint right away? Yeah. You conserve energy. You want to have a constant pace over time, right? So in cross country, your average velocity is probably pretty close to the velocity that you're running with most of the race. You don't usually speed up that much. Maybe at the very end, when you see the end goal and you know there's someone near you, you have that last kick, right? Where you put everything in there and you have like nothing left to give at the end of the race. So for cross country, for the most part, your speed or velocity is pretty consistent. The average velocity is pretty close to the overall velocity you carry while you run. It's not the same though for like a 40-yard dash. If you're running track and field or a baseball where you're running 90 feet down the line, when you come out of the batter's box in baseball, you have a huge acceleration and you get up to speed pretty quick and then you finish right through the line. Well, your average velocity might not be the same or might not be as close because you're varying velocity along the way. Or, this is an even better example. I'm going to use baseball because I coach baseball and it's an easy example to give. In baseball, when you're stealing a base, let's say hypothetically you're taking a lead, right? And you're waiting, the pitch goes through, you might take a little extra lead, and then the ball goes past the catcher, you automatically go for the next base. Well, you technically, doing this, leading off the base, you have a little velocity, the pitch is thrown, you get a secondary lead, you have a little more velocity, and then you sprint to second base. So in that circumstance, you had 3 different velocities. The beginning when you took the lead, a little more velocity when you got a little extra secondary lead, and then when you sprinted to second base, you have a much higher velocity. In this case, we are talking about the average velocity for the entire trip, not what I'm talking about as the instantaneous velocity. Okay, let's jot that note down. Instantaneous, the word instant, I-N-S-T-A-N-T, and then A-N-E-O-U-S. Instantaneous velocity is different than your average velocity. Okay, the bar over here, by the way, this little bar means average. Okay, this little bar means average. I use it a lot this year. Instantaneous velocity that you exhibit is not the same as the average. Instantaneous means the velocity at a given instant. That's all it means. Instantaneous, so in the beginning when you take your lead, you have a pretty low instantaneous velocity. Then your instantaneous velocity gets a little bit bigger because then you have a little bit more. And then when you sprint, it's very large. But the overall velocity from beginning to end is called our average velocity. And this is how we compute it. We take the displacement over the time. We don't care, and I don't care if it goes really slow, then fast, then slow, then stops, then really fast, then goes slow again, and then finishes. All that matters, beginning to finish, and the time it takes. It doesn't matter what happens in between. We're not focused in this course really on this term right here, instantaneous velocity. We'll see that a little bit later. And if you go on next year taking maybe physics or maybe calc and you want to challenge yourself a little bit math and science-wise, you will absolutely talk more about this. It's very important in your calculus and AP physics course. All right, let's take a look at an example so we can actually play a role. So during a race on level ground, we'll say that Jamie has a go-kart, she's driving it. It says her go-kart, she drives her go-kart with an average velocity of 6.02 meters per second. She travels east. What is her go-kart's displacement in meters after 2 minutes and 17 seconds have elapsed? So right away, I do this problem in the beginning of the year. I find that it's a rather simple problem, but it also makes you think a little bit. because there are some issues with the problem right away. And some of you might have seen it, but there's definitely an issue with the wording, with the units. Something's wrong that we have to manipulate. So I'm going to start this problem the way I start all problems, and I want you to take the same approach. So let's write this approach down. Step 1, list the given values. Write this down, please. And this, if you take this approach on all math-based problems in this course, you will really, really benefit, dramatically benefit. And this is the approach I'd like you to take when you're doing your homework for this section and when you're doing your problem sets that involve math problems. I always want you to take this approach. So list the givens. That's the first thing. List the given values. Second step, figure out or list or determine the desired value or the desired variable. What are you looking for in the problem? So what do you know and what are you trying to find out is step 2. Again, step 1, list the givens. Step 2, list the desired variable or the desired value, either way you want to say it. Step 3, and we're going to go through it obviously with this problem in a second. Step 3, choose the appropriate equation to use. Choose the appropriate equation to use. Just choose an equation. Pick an equation. Step 3. Step 3 again, pick an equation. Choose the appropriate equation, whatever shorthand you want to use. Step 4, solve that equation. Solve that equation for the desired variable. Solve that equation for the desired variable. So no numbers still. We have no numbers being used at this point. So all variables. That's why I had you guys work on the summer packet, solving for variables for that reason. Okay, and then the last step, I think we're on 5, right? Step 5 is just to simply plug in the givens to step 4. Plug the givens in to step 4. That'll give you the actual answer there. So let's go through this process so you can actually see it utilized. Okay, so step 1 is list the givens. So tell me what we know. What do we know about this problem? Give me some piece of information.
Average velocity is 6.02 meters per second.
And since I'm going east, Chris, is that positive or negative?
East.
Is east positive or negative? Positive. Think if you don't know your compass, draw it, by the way. North, south, right? West, east. Okay, it's always the word we. That's how I remember that one, by the way. I have people do like never eat sour watermelon. Have you ever done that one before? But then, you know what? But then I find that people don't know, wait, do I count it this way or do I count it that way? You know what I mean? So if you remember the acronym, but you actually go this way, then you're wrong, right? So you have to remember the acronym, and you have to remember, I know, but that's 2 things to remember. So I just remember the word we. I always say the word we. Whatever, that was when I was a kid. So east is considered positive, north is considered positive. South and west are considered negative. South and west are considered negative. Okay. What else do we know? Yeah, Alex.
It's 137 seconds.
So Alex, for now I'm going to write this, and then I want you to explain to the class now why you just said that. So Alex said 137 seconds. And I should stop writing SEC. I do that too often. This is not a 5. Make sure you see this. This is not a 5. I purposely try to make my S's a little smaller. Alex, why did you say 137 seconds, not 2 minutes, 17 seconds?
Because it says meters per second.
Okay, so why does, Thomas, explain to us why does that matter that it says meters per second?
So you have to convert the 2 minutes to the variable that you're using. Not the variable, the
Unit?
unit that you're using.
Very good. So here is my velocity. If this is in meters per second, then my times have to be in seconds. And this time was given in minutes, so 2 minutes is 120 seconds, plus 17 is 137. Let me show a quick unit analysis. I know you know how to do it. I know you all did in your head, but just to make sure we're clear on this, if I've got 2 minutes and I'm trying to convert it, this is like a side note. I'm going to multiply by a conversion factor. I put minutes in the bottom, seconds up top, 60 seconds per 1 minute. Minutes cancel. This tells me that this is equivalent to 120 seconds. Okay, so then you take the 120 seconds, to that you add the 17, and you get 137 seconds. That's the process that should be going through your head or shown. Honestly though, On Friday's test, if you convert minutes to seconds in your head, that's absolutely fine. You don't have to do that, show the work for it at all. Now, if you make a mistake and you don't get it right, you're not going to get the credit for that, right? So if you want to show work, you can. You're welcome to do that in the hopes of partial credit. But sometimes showing too much work like this wastes time also, right? Your tests are timed, so think about that. So if you can convert in your head, by all means, do the quick conversion. All right, so we've got our givens. Those are listed. Step 2, desired variable. What are we looking for here? What are we looking for? What are we looking for? What are we looking for, Gigi? Displacement. I'm going to write x equals question mark. And I write the question mark because it tells me that's what I'm looking for. You know, that's what the variable is that I'm trying to figure out. So we've got step 1 and step 2 done. All right, I'll put the numbers. I don't usually write step numbers. I'm just going to do it for this one example. Step 1, step 2. Step 3. Step 3. Yeah, what do we got?
Use the appropriate equation to use.
Which is?
V over T equal, sorry.
Okay, good. V bar equals?
V bar equals X over T.
Very good. V bar equals X over T. It's the only equation we have, which is nice, isn't it? So on this first test that you guys have coming up, it's really going to be focused on one equation, which is nice. If you look at your formula sheet under documents and handouts on Moodle, I mentioned this already, that formula sheet has like 50 equations. This is the first one and the only one that's on this test. So it's a nice test to, kick some butt in to get a good start off for the year, especially when it comes to, we're going to get into much more difficult stuff than what we're doing here. So X over T, good. That's step 3. What's step 4 tell us to do? What should we do next?
Solve for the variable that we want to figure out.
In this case, Chris, which one is that?
We're looking for x.
Yeah. So can you solve this for X? What would you do to solve this for X? How would you get X by itself? How would you get rid of the T is the question, right?
Yeah, would you multiply t on the side?
That's it. So think of this algebraically, right? We have to stop thinking about numbers for a little bit. If we struggle with this, you could plug in numbers at this point and solve. Like you could plug in for V and T and solve for X. But I want you to realize if this was X over 2, how would you get rid of the 2? Multiply by 2, right? Everybody, if it was X over 2, you would multiply by the 2. Well, it's X over T. So how do I get rid of T? I multiply both sides by time. And that leads me to step 4, which is T times V bar equals X. X equals T times V bar. Okay, I've taken the time, these cancel, and take a look. I've got that step right there. The last step of the whole problem is simply plug in. And because Alex and Tom helped us out with the units and converted our time into all seconds, we could plug in directly right now. If we didn't convert this to seconds, you can't plug in 2 minutes and 17 seconds and multiply it by 6.02. It doesn't make sense to do that. Those are two different parts. So again, we're going to use this time and this velocity, plug them both in right here, and we'll get an overall displacement for this problem. We'll get an overall displacement. So again, the time is 137 seconds times the velocity of 6.02 meters per second. Notice when I plug in, what do I show? Thank you. Very good, Danny. I always show my units when I plug in. The reason for that is because it's a mental check. What cancels in my units in these problems here? What cancels? Seconds. Seconds are in the top and bottom. Seconds are in the top here. Seconds are in the bottom over here. They cancel. My answer has units of meters, and that makes sense because it's displacement. 824.7 approximately. Okay, we will pick up with this in the next class. This is perfect timing. Listen carefully. Your lab is due tomorrow. It's been on Moodle for the last week. We started it about a week ago. So definitely get going on that. Make sure it's on time tomorrow. Do not turn it in late. I have not gotten a question yet about line of best fit. So I'm hoping we all know what a line of best fit is. That's part of your lab. You have to put a line of best fit through your data. Okay? If you did on a calculator, that's okay. Or if you use Excel, some people ask to use Excel for it. Okay, but if you have questions on that, you should probably ask me for tomorrow. For lab? Oh, yeah. Labs are always hard copies for labs. If you use a computer, just print out the screen. If you graph it on Excel, or if you graph it somewhere else, print it out, please. So last class we left off with that example, and now we're on the next slide that says velocity versus speed. Okay, it says velocity versus speed. And already we talked yesterday about the difference between displacement and distance. Can somebody reiterate what that was? Displacement versus distance?
Displacement is like from A to B, and then distance is like how you got there.
Very good. And the distance is the path traveled, how you got from A to B. Whereas displacement, it doesn't matter how you got from A to B. It's the straight line connecting A and B. Okay, the straight line connecting A and B. That's going to play a major role right here. So already we have talked about the fact that velocity, average velocity, is defined as displacement over time. We've already made this statement in the previous slide, but we're going to show how another formula is analogous to this. Okay, analogous to this. And this is something that I mentioned it yesterday, will come up again in your AP Physics and Calculus course, this differentiation between velocity and speed. So what I want you to consider is that if I walked around the room and ended where I started, we talked about this yesterday, what was my displacement? 0. So if I were to think about velocity, velocity is the displacement over time. So if my displacement is 0 ever, my velocity is also 0, my average velocity, right? Because the way you think of average velocity is how long it took you to get from A to B. But from A to B, if there's no gap, A is here and B is here, did I get anywhere? No. I may have walked around the room, but I didn't cover any ground, really. I didn't actually put any space between my starting and my final point. So that's why my average velocity is 0 technically, even if I do walk around and end up back here. Because velocity should cause me to move. And if I haven't really moved, like I end up where I started, I don't really have any real velocity. Along the way, as I'm walking, I absolutely have velocity. Positive velocity in the x, then I have maybe negative velocity in the y, then a little bit of negative velocity in the x direction, and then some positive velocity in the y direction, getting back to here. But the average of all those little velocities along the way averages out to 0, because I ended where I started. Okay, that's the big key about velocity and displacement. I'm going to go on to speed. Chris,
No, you just.
Okay. So speed is very, very similar, but just like displacement and distance had a little difference, we're going to see the same thing here. So let's write down our second formula here. And this is one of the few throughout the year that is not on your formula sheet. One of the very few, and you're going to see why right now. Because the formula is really the same as the one on the left. But instead of using displacement, what do you think I'm going to use? Distance. Exactly. Okay, so these formulas are analogous. I think that's how you spell analogous. I'm not the best speller, but I do my best sometimes. V bar equals x over t, or in this case, it would really be s bar, average speed, equals d over t. Again, d stands for distance. X stands for displacement. X stands for displacement. So along that entire trip that I just talked about, as I walked around the room, I had a given velocity. I also had given speeds along the way. If I wanted to figure out my average speed, for that trip around the room, back to the starting point, and is it now going to be 0? Like velocity was 0? Why was velocity 0 again? What was the rationale?
Ended up where you started.
Yeah, you ended up where you started, which made your displacement 0. But if I walk around the room and end up here, my displacement is 0, but my distance traveled is not 0. And this formula uses distance traveled. So if I do a lap around the room and it's, say, 20 meters, and it takes me 10 seconds, 20 meters divided by 10 seconds, my average speed is 2 meters per second. Whereas my velocity in that circumstance is 0. Okay, so I'll show you a quick diagram of that so we all see this. So let's take this path, and let's end up right back where we started. Okay? So the object itself ends and starts at that one coordinate on the actual path. Say you're walking, arbitrarily through Central Park and end up where you start. Now, the x value is absolutely 0. So v bar would equal 0 over, let's say the time it took you was 15 seconds in this case. All right, so that's my velocity, my average average velocity because I started and ended where I began. Now, my average speed, though, depends on the distance traveled. And let's say that the distance traveled along this path is 45 meters. Okay, so look at the difference in our answer, obviously. Okay, and 0 here, we're here with 3 meters per second. I made a statement in our previous class about the relative comparison or relative nature of displacement and distance. Does anybody remember what that was? We used an inequality symbol, actually. You can go back to your previous slides if you need to. I used an inequality symbol to compare displacement and distance for all possible cases. It's in your notes if you want to swipe up a little bit, you can see it. Can somebody reiterate what that was for us? I made a comparison using an inequality symbol that compares displacement and distance. Compares displacement and distance. Anybody recall what that was? If I didn't, let me know, because I should make that known. I thought I made that statement.
Isn't it change in distance doesn't equal the change in speed?
Correct. They're not equal, but with an inequality symbol. That's a non-equality symbol, actually. I know it's stupid. Like a less than or greater than symbol I'm talking about. So what was the statement? You're right. They're not always equal. They can be equal sometimes, right? If I walk from here to here, my distance and my displacement are the same, right? But they're not always equal. There was a general statement with inequality. Yeah. So let's reiterate that in blue or yellow or green or something at the bottom here. Let's use yellow. The distance traveled is greater than or equal to the displacement. The distance traveled is always greater than or equal to displacement. And we came up with that corollary or that idea after thinking for a little while about this. If I walk in a straight line, these two things are absolutely equivalent. If I walk in a perfectly straight line. But the minute I take a curved path, my distance is the curved path, right? Imagine I'll draw it for us so we can see this. So the minute I take a curved path from A to B, my distance is the black line and my displacement is the red line. I'm drawing the diagram up here on the top right. Again, remember, walking along a curved path, the distance is the curve, the displacement is the straight line. So this holds true to what we just saw here, where distance is greater than or equal to displacement for all possible cases. So what can you tell me, analogously, about velocity versus speed? About average velocity and average speed. What could you tell me there also? What could you tell me there? Yeah?
Velocity directional, and speed is
Correct, but I said about the relative nature, right? How do they compare to each other? The relative nature of speed and velocity. Yeah?
The speed is greater than or equal to the velocity.
Yeah, and I'm going to use absolute value symbols, but that's exactly it. The speed, just like we had distance is greater than or equal to displacement, we're going to see that speed, average speed, is greater than or equal to average velocity. Now, for a reason, I'm going to do this. I'm going to put absolute value symbols around this stuff. And I really should do it for the other one as well. Okay? I'm putting absolute value symbols around stuff. Now, the reasoning behind the absolute value is that sometimes your displacement and your velocity can be negative numbers, as Spencer told us a minute ago. Right? This matters the direction in which we travel. So these can be negative. So I'm comparing their magnitudes, really, how much they are physically, not the direction they're going in. So again, our speed was 3 meters per second. Our velocity was 0. This statement is true. The speed is greater than or equal to velocity. Both of these statements are always going to hold true. Now again, when are they going to be equal? What's the one case that they're equal to each other? The one case that displacement and distance will be equal, or speed and velocity will be equal, there's only one case that that'll happen. Well done. If you walk in a straight line. If there's 0 curvature whatsoever to your path. Okay? And again, just look at this example right here. If the curved path D didn't exist, but the path you took was the red line, well then your distance and your displacement are absolutely the same, aren't they? So if your distance and displacement are the same, look at your formulas. Displacement gives you velocity, distance gives you speed. Well, if the distance and displacement are the same, then these are also going to be the same. So there is a chance they can be equal. That's why we put greater than or equal to for both of these scenarios. All right, let's move on. That's our velocity versus speed. Let's recall this concept from last year, or from, well, technically 2 years ago when you looked at graphs in Algebra 1 or Algebra 2. Recall that the slope of a line indicates its steepness, aka rate of change. And I wrote right away analogous to velocity, because what is velocity? What is velocity? It's the rate at which you are moving, right? It's a rate of change. That's what velocity is. I'm changing my position at a given rate. That's what velocity, ready? Really slow or low velocity is a slow rate of change, like a grandpa maybe walking down the sidewalk, versus somebody walking a lot faster. Their rate of change, they are changing their position at a higher rate. So since steepness and rate of change are really the same thing, we can look at our graphs to help us with this concept. Okay, we've got our graph. So before we get into this piece here in the box, let me draw a graph. Okay? Let's draw a graph. We'll just draw the first quadrant. And let's put along the vertical axis, we'll put displacement. And along the horizontal axis, I'll put time. You saw this in the first lab you just turned in, right? That your y and x axis are obviously not always called y and x. Right? It was C versus D in your lab that you turned in, circumference and diameter. Well, in this problem, remember that x represents what again? What word? Thank you. Displacement. It's not like I'm suddenly making the vertical axis my x-axis. You see what I mean? I'm not calling these x and y anymore. I'm done with that. In your math class, you absolutely will. And then you might actually use other graphs and other nomenclature later in the year in math. But in your math class, traditionally it's x and y. Don't let that confuse you right now. This is not an x-axis here. This is your displacement axis, and this is your time axis. And if you recall from your summer packet, you actually analyzed the graph like this. You had two graphs in the summer packet. This was the first one in the summer packet that you looked at. And you did that for a reason. I wanted you to get used to it. We're about to do that right now. What are my units of displacement? What are my units of displacement? Or distance. They have the same units. Displacement and distance. Meters. Very good. I'm going to put that in parentheses up here so I know my units are meters. And what are my units of time? Seconds. Now, if I think about slope is rise over run. I don't want to say forget. In your math class, you can use delta y over delta x, right? y2 minus y1 over x2 minus x1. That's like the way you learn in math. But I don't want you to confuse this letter x here. So the way I have you thinking about it is the change in the vertical coordinates over the change in the horizontal coordinates. Okay, so in this problem here, if I want to figure out what the slope is, let me choose 2 points. I'll put a coordinate here, and I'll put a coordinate here. I'm going to label them. I'll connect them with a straight line. I will say here that this is a coordinate of 0, 5, and this coordinate is 12, 55. And I'm picking arbitrary numbers right now, as you can see, right? I'm not even labeling my axis. I'm not even labeling increments right now, because this is just for us to think about this particular example. When we draw graphs, though, we should label our axes, right? Put increments on them and such. We have our axes labeled with these. Now, for this problem, if I want to calculate the slope, it's the change in the vertical coordinate, which in this case, remember, is the second coordinate, divided by the change in the first coordinate, or the horizontal coordinate. And if you weren't sure going into this which was which, well, 0, right? I don't move left or right, that's the 0, and then I move up 5. So that's representing this 5 up. This 55 means this is 55 up. This is 12 over. Okay, so keep that in the back of your mind. I'm not putting tick marks, so we should know which coordinate represents which axis. So my slope would be my change in my vertical, which will be this 55 right here, minus the 5 that it started as. and those units are going to be meters, divided by the change in the horizontal, which is this 12 minus the 0 here, and those units are seconds. Again, the vertical component is the second coordinate. The horizontal component is the first coordinate. This is always the way you've done slope in your life. You just are not calling it y2 minus y1 over x2 minus x1 now, because I don't want you to confuse this x with x on its axis. Now, with that said, I can calculate this, right? We're going to get 50 over 12, so around 4 and change. And my units are meters per second. And I know my units are meters per second because 55 minus 5, well, that was given in meters. 12 minus 0, those units were seconds. So if my units are meters per second, and what do we know meters per second represents? What does meter per second represent? Velocity. What we can gain from this information is that the slope, this is our conclusion, the slope of a displacement time graph is velocity. The slope of a displacement time graph is velocity. If the slope is higher, what does that mean? If the slope is like this, right, steeper, what does it mean about the object now?
Higher velocity.
Higher velocity, it's moving faster. What if the slope is this, right here? What if it's a constant function or a flat line? What's the slope of a flat line?
No, there's no velocity.
Yeah, there is no velocity, it's 0. And that makes sense because look, ready? If my position, remember this is displacement or position, if my displacement is at 5, and it remains at 5, and it remains at 5, am I moving? No, my displacement isn't any different. There's another word for this graph, write it down please. Some books will call this a position versus time graph instead of displacement versus time. Jot that down. Okay, it's on standardized tests, it's on AP exams. They'll use both of those phrases interchangeably. So a displacement time graph or a position time graph could be worded interchangeably. And I might use either one on the test. Although it's obviously displacement, because x represents displacement, it is sometimes called a position time graph. Think back, what was the definition of velocity in our formula? V bar equals, what was it? What was the first formula we learned? V bar equals? X over t. And take a look. When you find the slope, isn't it just x over t? Isn't this the change in the displacement, or x, over the change in time t? So when you're finding slope, you're using, technically, x over t, actually, in this formula. This is your x, that's your rise. This is your t, that's your run. So you're really actually just utilizing the same formula, but you can just do it by finding the slope instead. Find the slope instead. Okay? So this is what my slope becomes. So inherently, my velocity equals my slope. Now, I'm not going to go crazy with this because this course is not a calculus-based course. If you take AP next year, you'll see things in physics that involve more curvature to them, not just linear functions. But the same thing applies for anything that has a curve to it. So if I had a graph like this, okay, right there, in the red curve right there, and I wanted to find the average velocity from A to B, from this point to that point, you can connect them with what's called a secant line. Secant. Remember from your geometry class, a secant cuts through a circle in 2 different locations, whereas a tangent in a geometry class would touch the circle's edge only once. This is similar to a secant. So if you wanted to find the average velocity of the motion represented by the red graph, you just connect them like that. And you think about the slope from here to here. That gives you the average velocity. This person, if you want to know what they're doing, if you want to take a look up, this might help you to understand a little bit more. This person is moving pretty fast because the steepness of this line starts off really steep. Then they start to slow down, until at the end, what are they doing? Yeah, 0 velocity, they're standing still. But from here to here, they had some velocity, right? So if you want the average velocity, just get the slope of the blue line. So again, this is an example of a person that's doing this. Fast, slow, stop. Yeah, at the end I've got no velocity, but the whole way through I have velocity, didn't I? So you can calculate the average of my velocity, again, by finding the steepness of the blue line. Okay? If you're ever given two coordinates on a position time graph, just find the slope between them, and you've got the average velocity. When would the average velocity be negative? What kind of a graph would I have to draw for the average velocity to be negative? For it to be negative? Alex? Yeah, a line with a negative slope. So the function is no longer increasing, but it's a decreasing function. I'll draw that in yellow so we can see what I'm talking about. So an example like this. Okay, because the slope is clearly negative, the velocity in that example in yellow would absolutely be negative. Absolutely be negative. And think about it, because watch. I'm starting at a position of, say, what looks like above 55, right? So say 60 meters away, I'm starting. So let's call the desk the origin, and let's make believe this is 60 meters for a second. I'm 60 meters away, and then it looks like 12 seconds later, now I'm only about 10 meters away. So I've walked all the way here to about 10 meters. Which way did I just walk? Left or right? And what did we say yesterday? Left is? Negative. So think about this. This means that I'm starting 50 meters away, or 60, this is 55 actually, so this is probably around the same. And then I'm ending over here, which is pretty much at the origin or starting point. Okay, we're going to do more of this. Unfortunately, I don't think we're going to get this next lab in before this test, but on the next test, we do a lot with acceleration also. So the next lab is going to be using motion detectors. You're going to work with like another person, the two of you, and you're going to actually have to move and track each other and use these. So we're going to use these a lot this year. We're going to be using these LabQuest devices to collect data to see your motion and see what the graph looks like. And they're very friendly, they're very useful if you use them properly, and we'll see on the next test how we're going to actually show this with a position time graph. Okay, on the next, but this will be not until the next test, we'll see that. With that said, let's do two final examples for today. Let's do two final examples first. This is one that I think most of you probably would get pretty quickly because we've gone over this a couple times now. A book is moved on a table around the edges, and the table dimensions are 1.75 meters by 2.25 meters. If the book ends up at its initial position, what's the displacement? If it completes the motion in 23 seconds, what's the average velocity? And finally, what is the average speed? So spend about, spend about 3 minutes by yourself, the person next to you. If you want to draw a diagram, please. I know some of you might get it right away, but try to list givens, right? Try to write out the formula. I want you to take the approach that I've taught you. List your givens. What is the unknown that you're looking for? Choose the formula. Resolve that formula with variables. Then plug in the numbers. Go through those same 5 steps from yesterday. Okay, with this kind of a problem. And again, check with the person next to you as you're going through it. I'll spend about a minute, wait, and then I'll put the answer, or I'll start writing up what I think should be up there. If you're confused a little bit, if you want to ask a question right now, it's a good time to do it too. Come by and help you individually for the trouble. If you're working by yourself, that's fine, but when you're done, check with your partner or person around you, please. Jack was in this class also? Jack was, right? Did he say here that one day? Are you listening? You guys talk to him? Anybody talk to him all from school? You have talked to him? I don't want to practice, so I just want to know.
I think someone who's like averaging projected 13.
Spencer, did you give your own individually?
Yeah,
You have to give your own individual write-up, so you know. So you have to turn that in tomorrow. Hey, make sure you're doing your own write-up, but I do like that you put both names up here. You should be putting your group members' names on your lab. So if you want, I'll give you right now if you want to put them on there. because I do like to check your data, and when I do check your data, it's with your own group member. So just put your name again of your group member in parentheses after your name. After your name, put your group member's name in parentheses, please. I'll come back around and pick them up. Again, put your group member.
Basically, the distance travel
I'll come back around. That's what I did. Put your name in for now. We ready to go over? All right, I'll give you another minute.
So just to read that,
Alright, you don't have to look up yet. If you're not done, I'm going to start putting what I think is right up here. You don't have to look up if you don't want to yet. So my only known is the 23 seconds and the dimensions. I also know that you start and end in the same spot, right? And then my 3 questions are these 3. All right, so first question. What is the displacement and why? What is the displacement and why? Is the first question, Caleb?
The displacement is 0 because it ends up in the same exact spot.
Well done. The displacement is the part that you should know is 0 because it ends up where it starts. Very good. The book starts and ends in the same spot. So there's no work needed for that. That is what I would say by inspection. By looking at the problem, you know the answer is 0. Okay, when I say by inspection, you can do that. Second part. Technically, there's no real work needed, but what would the formula be to figure out average velocity? I want the formula. I know there's no work needed.
X over t.
And in this case?
Goes 0 meters over 22 seconds, which is 0.
Very good.
Meters per second.
Okay, so yes, the answer is definitely 0, but please show me some rationale behind that, and that's your rationale. Displacement over time, but your displacement was 0 meters, and your time was 23 seconds. And then finally, speed. Speed, what's the difference, Danny?
So we traveled 8 meters.
So where's that coming from, Danny? D equals what? Where are you getting the number? Just so we're all clear. I know you got it.
It's
Perimeter.
This is over time.
Okay, so you're getting 8 meters, but where's the 8 meters coming from, Danny? Just tell me that part.
So 1.75 times 2 plus 2.75.
Very good. We're just doing the perimeter of a rectangle, right? To see the distance traveled. This problem was a very simple one with linear segments. If it was a circle, what formula do you use to find the distance around a circle? Circumference, right? 2 pi r or pi times diameter. Formulas that need to be known from last year in geometry class that are not on a formula sheet. Circumference of a circle, area of a circle, perimeter of a rectangle, area of a rectangle. These need to be known, okay? Because any shape could be given on this test. It's not going to be an amorphic curved shape that you can't actually figure out, okay? It'll be something that you can actually figure out the perimeter of. By the way, circumference is the same thing as perimeter, right? We know that? Circumference is just a fancy word for perimeter. So, Danny, keep going. What was the final answer you ended up getting here as a decimal, I guess?
8 over 23 meters
8 over 23 meters
per second.
per second. And you can leave it like that. Okay, you can give me a decimal approximation if you'd like to, and if you're going to round it, give a little symbol that shows rounding. As a decimal, give me like 2 decimal spots for this one. What do you got, Spencer? 0.35 meters. I'm not even going to focus on sig figs this year at all. I'll tell you that now. So I'm just going to tell you specifically on the test what to round to. Okay? If it's a problem that involves things on a microscopic scale, I'll definitely say to the nearest 10,000. So you need to know the names of the places, but I'm not going to have you doing sig figs. So why might it, please listen, why might it be beneficial at times on a test to actually calculate an approximation and not leave it? Now, you're right, Danny. 8 over 23 is absolutely right, and I would accept it for 100% on the test. But what benefit could you have from actually calculating an approximation, even if you don't write it down? Maybe you're just doing your calculator, 8 divided by 23. Okay, 0.35. How is that going to help me on the test? Sydney?
If it's like ridiculous.
Thank you. If it's a reasonable answer, and this is. Think about 0.3 meters. What's a meter? Can you give me an idea of a meter? Meter sticks? How big? Show me with your hands. Yeah. Meter sticks are about this big. If you hit each other in the face as I say that, nice. If you were to spread your arms out, you know that your wingspan is about your height. You guys know that one? Mm-hmm. Bodies. So your wingspan is about 2 meters for the average person. So if you think about like just about this much is about a meter. So 0.3 meters. 0.3 meters, it's about a foot. So that means we're moving this book this fast every second. That is physically reasonable, right? If I get an answer of 27 meters per second, that book is like a bullet. 27 meters, I mean, this room across is not even 27 meters. Yeah, this room across is about 10 meters across. A big step is about a meter, by the way. A pretty decent sized step like this, like a full step, is about a meter or so. So this is about 10, 15 meters across, 27 meters per second. The book would go from this wall across the street, hit the bricks in 1 second. It's not going to be moving that fast when you're physically moving it around the table, right? So use the context of the problem to make sense of your answer, as Sydney told us. Questions on this one at all? All right, let's go on. Example 4, we have 5 minutes. If we don't finish this homework is still due the same day. Now, notice for you guys, I made this homework due tomorrow. I don't meet with you tomorrow, obviously, right? Because the problem set is due on Thursday. So I didn't want to give you double homework on the problem set night. So tomorrow, how are you going to submit this? Yeah, it's got to go to Drive. Unless you come by my office tomorrow and just put it on my desk. That's fine also. So if you want to come by, drop off the homework as a hard copy, that's totally fine. But make sure you do it on your own. I'm not going to seek you out. Okay, so put the homework in Drive if you don't see me tomorrow.
I have a question about that. So I've been doing my homework like on a separate notability. Is that
yeah, it doesn't have to be at the end of the notes.
Does that have to be the end of the
No,
notes? Okay.
some students do it one way, some do it the other way. It's fine. All right, 2 students walk in the same direction along a straight path at constant velocities. One of them slower, one of them faster. Assuming they both start at the same point at the same time, how much sooner does the faster student arrive at a destination that's 500 meters away? Okay, a pretty standard math problem you would have seen in 9th grade. The very basics of physics is really math, right? So we're seeing that this should be a little bit of a review from something you've at least seen at some point in time. So if you're having trouble, you start with a diagram. And in my mind, a diagram might look like this. I've got student A, student B, they're both moving. This is the 500 meter mark right here. And when this person's at the 500 meter mark, it looks like this person is somewhere behind. Right? One's moving fast, one moving slow. That's kind of all I really know about this. I know the velocities, so I can write them out. For both students, the displacement is the same because they're both trying to finish this race, if you will. So the displacement is 500 for both of them. It doesn't say figure out how much far behind in distance one student is than the other. So we're not trying to find the displacement of the second student, but we could do that if we wanted to. We are only concerned with how long it takes the second person to finish after the first one has already finished. We're looking at, in this case, what variable then? How much longer? What variable is that? The units are seconds, correct? Dennis? Time. Very good. So the question at hand here is time. Now, I didn't write velocity down as a given because I need to talk about that. How many different velocities do we have here? Yeah. So what might I do to signify that I have two different velocities? I can't call them both V-bar.
V-bar 1, V-bar 2.
Yes, subscripts. Subscripts are huge in this class. The faster student, or let's go with slower. The slower student is moving at 1.5 meters per second. The faster one at 2.0 meters per second. So it is important in a problem like this to use the subscript to differentiate between the two different people, objects, students, whatever it may be, cars, who cares? So I want to figure out the time it takes one student. I want to figure out the time it takes the other student. And what do I want to do at the end? Yeah, by what operation in math? Subtraction, right? Find the time it takes each student and just subtract them. And that's the difference in the time it takes them to finish. Again, we are not figuring out physically how much further back is Joe Schmo who's walking really slow, right? This guy might be like 100 meters back. I don't know. I don't care. It's not asked in the problem. So there's no need to figure out the displacement x of this slow person when he gets here or she gets here. All we care about is time. My formula that I use, only got one so far. What's the formula? Same one we've used the last 4, 6, yeah? Yeah. Now, my goal is to figure out the time it takes. So what do I do here now?
Well, you just have to do it for both of them.
But if I want to solve, I'm saying, what am I solving for?
Oh, you're solving 3, so it'd be t equals x over v.
Let's pause there for a quick second. Does everybody see that again? Remember, I multiply up by t, and then I divide by v bar. So inherently, what am I doing with these two variables? Switching them. This happens over and over. That's why I tell you just to remember to switch them. Yes, you are definitely multiplying by t and dividing by v bar. You are doing that, but no to switch it. How many times do I have to do this? Twice. This is my formula. So I have to do this 2 times. I have to find out t1, and that's going to equal x over v bar 1. And then I have to figure out t2, which is x over v bar 2. Okay, we'll end up getting, listen real quick, you'll end up getting 2 different times. And what are we going to do with those times again, Alex? Subtract them. Okay? Your homework is on the next slide. Okay, make sure again this gets done tonight. There are, looks like 7 problems. It may take you a solid 30, 40 minutes to do this. Persist. Don't give up if you get stuck. Ask me, ask a classmate, come by for help. Even if you don't get all the homework done, you can come by to office hours tomorrow with questions.